Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
I'll just start with the first question. In deep learning, there's a lot of papers that you see that are, improvements to the sort of learning algorithms, right? Small changes or, important changes we've seen this morning, which are, you could say, are sort of plumbing, right? We need these algorithms to work really well, and what do we do to make them work really well? But there might also be fundamental research questions like, what don't we yet understand about deep learning? And I wanted to ask everyone here if, what they think about sort of what is important between those two, but also if you can identify a sort of fundamental problem that you would really like to understand and you currently actually don't understand, and maybe, encourage other people to find an answer for. I guess we just go sort of, in sequence. Joshua, you want to start? You have the microphone, so that's a...
Why don't you go ahead?
Oh, you're not in? Okay.
Does it work?
No, it's not working.
For me, a very interesting question is how do we expand the computational capacity of the networks that we are now using? It's possible to do many interesting tasks like classification and so on with the current feed-forward neural networks. But for instance, problems like segmentation, reasoning about relations and so on, most probably require representations that are more expressive than what we have now. I think it's a very interesting question how these can be built into the current systems.
Okay, for me, I think how to learn the network structures, especially the connection of the neurons. What kind of neurons they should be connected. So far, you can see the most widely, most successful net in computer vision is ConvNet, and its connection is based on the spatial neighborhood, and if they are close in space, they are connected. But I believe that probably there are some other criteria and to model the correlation between neurons to find their connection properly. Also, there are some neurobiology evidence showing that. For example, you look at the human brain at 6 years old, it has many connections between neurons, and when it grows up, and some connection just disappeared. So why this happened? It means that probably the ways and the network, they are jointly optimized. It's not simply designed manually. I think probably this is worth for the future study.
Yeah, one of the questions that is very interesting for us is the ability to ingest all the labels that exist. So, for example, if you can have a lot of data, a small fraction of that data is going to have labels. So, for example, for images, you're going to have some images that have category labels. Some of those images might have bounding boxes. A very few images are going to have segmentation masks. For videos, you're going to have more variations of this. For other domains, you're going to have more. And the question is, what is the principled way to take advantage of all these labels, where some of them are costly to obtain, but even perhaps a single bounding box can give you a lot of information. So what is the principled way of taking advantage of all this?
Yeah, I actually agree with what Sergey was saying.
Model the joint of all of them.
Yeah, I agree with what Sergey was saying in the sense that I think we don't know how to combine all this sort of disparate supervision together in a really efficient way. And it just feels like we should be able to do better, that our models with, just a few more examples can use all their existing knowledge to generalize to these new examples and incorporate all these extra tasks. We just don't have good frameworks to do that at the moment, I think.
I'll give two answers that I think actually follow in the spirit of what the previous speakers said. First, I'm just going to copy what Joe Bates said a minute ago when he asked me the last question of how do we integrate all these things together into a single greater competence. I think that's still an open challenge and one that I look forward to. And then maybe a related comment or future challenges. I'm specifically interested in if we can have these architectures learn more the way children learn or more the way people learn, leveraging what we know from cognitive science, especially as we get into the realm of these joint vision and language models. If we're teaching a new term to it would be nice to be able to teach a new word to these models, you know, with 3 or 4 examples, the same way you can teach a 3 or 4-year-old. And so there are models from cognitive science and concept learning models, and it'd be interesting to see if they can, you know, see how they can be brought to this world as well.
So one direction that I'm really interested in and seems very difficult is something I've been talking about a lot, but we haven't really found a lot of good solutions. I think Hong Lak presented some things in that direction at this NIPS, which is how do we discover representations that capture the underlying causes of what we observe. And the reason this is important is that if you want to generalize to really new situations, the only good way of doing it is by having a kind of implicit model of how things unfold in the world. And that sort of is not something we're paying enough attention to, I think, and probably is more in the realm of unsupervised learning, but can use any sources of data we have, including labeled as cues for what are the underlying causes.
That's a nice bridge to the next, top-rated question here, unsupervised learning. So there's been a lot of excitement in unsupervised learning. Lots of people are working on it. But it's not so trivial to actually figure out how to evaluate whether your model is doing well. So some people report probabilities on test data. Some people look at pictures and they look pretty. The prettier the picture, the better the model. So the question is, how do we evaluate unsupervised learning? And how important is unsupervised learning, do you think, for deep learning in general?
So it's an open problem, and I think we should work more on it. One interesting thing that has showed up recently in some papers with generative models is we show the generated examples to humans, and they're supposed to figure out if these examples are coming from the machine or are coming from the true distribution. Of course, the problem with this is the machine could just cheat by remembering examples by heart, so you have to make sure you have a way to counter that by comparing with training examples, and that's also a common practice. One interesting twist is to train a model to play the game of the Turing test by trying to discriminate between the generated examples and the training data, and that's one of the ideas that we've been pursuing in my group, and Ian Goodfellow has been leading.
In terms of a serious answer, I don't really have one except to see how well the unsupervised representation transfers to other tasks, but that seems to be a bit of a cheat.
But with which tasks then? That's interesting.
Yeah, that's why I said it's a bit of a cheat.
It's part of the story. I mean, ultimately, that's what we want. So we want to have these tests.
My facetious answer is I just show the pictures to Alyosha Efros, and he tells me if they're pretty, and then I know.
Okay.
I think that unsupervised learning without any other reason is useless. We should always do it for a purpose. So if we are trying to have good classification, then we can measure how well unsupervised learning is helping classification. If we want to do compression, then we can measure compression, and so on and so forth. Denoising is something that we use for measuring how well the network had learned the underlying distribution, but I'm sure there are others. But yeah, I would recommend you to always do unsupervised learning for a good purpose rather than just for a paper.
Yeah, I mean, exactly. What is the point of doing unsupervised learning? The point is to actually maybe then take your model and apply it to the task you're actually interested in.
But what if you want to apply it to many tasks or to tasks that you don't know yet that will come in the future?
Yeah, I mean, it's not an easy question. I think like trying to do some unsupervised learning on a model, then test it on a suite of tasks, does it do better? Like that's really what we're after. We don't really care if the images look pretty or not, like although it looks really cool. So that's what I would say.
Yeah, I don't have much to add to what the previous speakers have said. So if we can train a good representation and then realize that we can actually use that to train the best classifiers and localizers and whatever else, then that's a good representation, and we can use unsupervised learning just because we have a lot more unlabeled data than labeled data.
Yeah, I agree that both unsupervised learning and supervised learning, the goal is to learn the representation, which can separate or disentangle all the factors. Best thing you can get this kind of representation, you can just apply using a simple SVM or linear classifier. You can solve this kind of a classification problem. So I think even for unsupervised learning, so whether you can separate these factors. Also, I hope that they can also achieve some invariance. So for example, our human, when we watch, we can manipulate this object to watch the multiple views and also can track objects. We hope that the feature has some invariance if we move the objects and in scale and the viewpoints. And so far, based on our experience, if you track the object, you look at the, for example, detection score, you can see that the current feature changed dramatically, which is not good. Yeah.
I would just like to comment on Joshua's comment. If we have an unknown task coming our way, I don't think it's very much different from held out test label. So we can just have held out tests.
Task, right. So it seems we can take this as a recommendation for the field to come up with a good test suite for, testing our unsupervised learning algorithms, because right now I think we still need to do that. So maybe another related question is, so how far can we get with deep learning? In other words, in AI, in terms of solving AI problems, so we have like, logical reasoning or first order logic. I guess we haven't quite integrated that fully in deep learning, although people are working on it. So are there particular fields within AI that would really need some really new ideas in order to be tackled? And not everybody has to answer, I guess. If you have an idea about this, then.
I think that deep learning has been able to do something, a part of what human cerebral cortex is doing, but only part of it. And I think that there are many other things that, like basal ganglia and so on that we haven't really tackled at all. So I think that we are just scratching the surface here. Definitely things like reasoning, symbolic reasoning, is something that we can do. I'm not saying that we should implement symbols as symbols, but like sub-symbolic representations of symbolic reasoning, I think, are definitely going to be there. Okay. And we don't have that like now.
Anybody else who wants to comment on this, or? No? Okay. So if anybody, sorry. There's a question by Jürgen Schmidhuber. Go for it, Jürgen.
Hey, Max. Thank you so much. I would like to add something to your most popular question.
Talk in the microphone, please. It's not very clear.
Can you hear me? How do I do that?
Just talk in the microphone.
Can you hear me?
Yes, that's good.
There we go. I would like to say something on your most popular question, and as the panel wasn't very sure what to do with it, but I think it's totally clear what is the purpose of unsupervised learning. You want to compress the data. You have a lifelong history of observations and actions, and then part of this history is regular. So you want to figure out these regularities. How do you measure whether you captured the regularity? Well, you see whether you can compress it, for example, through predictive coding. So you have, for example, a recurrent network, which takes as an input all this history and tries to predict the next thing. How do you measure the performance? How do you measure whether you have a good unsupervised learner or a bad one? Well, you just use minimum description length. So you look at how many bits do you need to encode the recurrent network or whatever you have that is doing the predictions, plus the deviations from the predictions, the extra bits that you need for compensating for the errors of the model. And then the total number of bits, standard minimum description length, gives you a quality measure of how good that unsupervised learner is. Now, what can you do with it? That is then the second way of evaluating the thing. You have to solve problems in reinforcement learning or supervised learning. Now, you can take this thing as a preprocessor and feed it into your reinforcement learner or unsupervised learner, and then you measure, can it learn more quickly or faster? And there have been many examples over the decades, since 1990 at least, where both reinforcement learning and supervised learning became better through these unsupervised pre-training stages. So I think it's not really an open question. We can certainly improve the methods for doing unsupervised learning, but at least the objective, I think, is pretty clear.
Okay, thank you for your contribution. Is there any people who have questions for the panel? Please go to the microphone. Otherwise, I'll just go down the list. So one question could be, can we learn something from biology? Are there things from biology that we can get inspired by? Maybe, yeah. Yes, sure. Yeah, go ahead.
I just wanted to comment on Jürgen's comment about compression. I do agree that in some cases compression is very important, but then we are always limited with the amount of representations we have. So I don't think that compression is necessarily a good idea if you have a certain type of information you want to represent and process. If you know anything about the relevance of information, you should take that into account. And we are not really interested in, often we are not really interested in compressing or representing the original images, but rather we are interested in using them for some purpose. So I think that compression is nice if you have unlimited resources, but otherwise not.
Can I say something on that, or better not?
Yes, you can, but keep it a bit short, maybe.
I'll try my best. Yeah, so what you are referring to is really the usefulness of the data, and of course that is the primary thing that we are after. We want to just optimize the policies of our reinforcement learners and supervised learners and so on, and then the true purpose of unsupervised learning in that context is just how well does it help our supervised learners or reinforcement learners to solve the problem. That's true. On the other hand, all of science is really just about finding regularities in the data, and all of science is a history of data compression, basically. Whenever you come up with a law such as when you invent gravity, for example, or the law of gravity, you discover that you can greatly compress through predictive coding all these falling apples, which always fall down in the same way. And that means that you can greatly compress. And that's really useful if you have the code for that, for solving all kinds of problems that are connected to falling apples.
Okay, so let's keep it at that. Thank you. So was there another question, maybe? Peter?
Yeah. So in the last few years, we've seen huge progress in deep learning, abstract representations of sensory data, of perceptual data. But we haven't really seen the same movement on the motor end. There hasn't been a huge application of deep learning to learning abstract motor representations or ways that an agent can interact with the environment. So I'm wondering, what do we think is missing? What's the research direction we have to go in to achieve agent that can actually intelligently interact with a real environment?
Well, I would direct you to Peter Beal's talk this afternoon.
And a
panel there. I think there's still a lot to be done on really high-level abstract reinforcement learning, but there is progress.
Anybody else?
We need people like you to work on it.
I think that hierarchical reinforcement learning is a hugely important topic. We're working on it. I think many other people are working on it. And I think that understanding how we can compress and generate sequences is one important part there, because eventually what we want to have is high-level representation of complex action sequences or complex interactions with the environment.
Anybody else wants to comment?
Yeah, I guess maybe data is another big issue. So if you want to model the interaction between the agent and environment, you have to also collect a huge amount of data. You know, in the deep learning, so it's kind of data-driven. You have the image net, we have the learned representation. So we probably need that kind of data set.
Okay.
Thank you.
Okay. Anybody else wants to ask a question? Otherwise, I will ask questions. Okay. Yes, please go ahead.
Hi. We keep saying that we would like to the deep network to learn like a child, and I was wondering if there is any reason to believe that the ladder of difficulty is the same for deep networks and for children. Typically, right now, we could evaluate the difficulty of a task by computing how many bits of information you have in the network. So the question is the degree of difficulty the same as it might be for a child, according to, for instance, to Piaget or something?
Is there anybody who can answer this?
Maybe you can rephrase your question. What did you mean by the number of bits of information in the model and how it relates to the rest of the question?
Well, I mean, if we are considering a deep network as a program, we could evaluate what is the complexity. Am I right so far?
Right.
Okay, so then we can say that we can compare the difficulties of different tasks, right?
Under
we
what
could
measure?
say that typically recognizing a face is something, and trying to predict an action is something else.
You mean like the number of, the size of the program that's needed to do that task? That's what you mean?
Yes.
Uh-huh. And what's the question?
And then the question is that we know that the children, they are learning in phases, right? There are some activities, there are some skills that are acquired before others.
Right, right. So I think this is a very good question. In machine learning, we tend to have a model of learning which is very, very simplistic, where we show all the examples in random order, and it fits well a lot of the ideas we have about learning, but it's not at all how children learn. And so there's a realization, maybe because of optimization issues, but maybe for more fundamental reasons, where people see that it's sometimes better to train in a sequence of tasks rather than directly the task of interest. And so some people call that curriculum learning, and there are other names, but basically we don't know how to do this well. It's more like heuristics that people use in order to help training models, which otherwise seem untrainable. If you don't use these kinds of, you can think of pre-training as different forms of pre-training as an approach to that. But we don't understand this nearly enough. So I think it's good if more people think about it.
Yeah, I think this is going to become more of a thing, curriculum learning, as we get more and more complicated tasks, and you can't just cold start things, and you need to start introducing a curriculum into your learning. And these are all open questions on how you do that effectively and how you have this continual learning without forgetting.
There's some more questions there.
Hi. Related to the idea of trying to get more sparsity in networks, and also just bringing some neuroscience in, I was wondering if anyone's looked at trying to come up with the concept of different types of nodes. So in layer 4 of the cortex, you find that there's specific cells that make connections only to other specific types of cells. There seems to be some types of rules about how cells will connect in that way, and that imposes a type of sparsity in the network. And is this something that anyone's been thinking about? And do you think it might be useful?
Well, if you look at a lot of the progress recently, people design architectures, so things like neural Turing machine, memory networks, and the kind of data structures that people tack on normal neural nets, really, or LSTMs, for example. They all like specialized architectures which seem to be very useful in a number of tasks. I don't think we have a big picture of where to go next, but it seems important. This exploration has been very, very fruitful, and it corresponds to different roles for different types of neurons in these artificial neural nets.
Somebody else who would like to say something? No? Maybe Kevin wants to ask a question.
Yes, this is a question primarily for Valpola, but I think Max might be interested. I'd be interested in Max's opinions as well, which is, so in Harry's talk, he was talking about EM and variational inference and Kalman filtering, and then he said, let go of your inner statistician and let's blur the model algorithm, model inference distinction, and just treat it as a circuit. Can you talk about the pros and cons of that compared to more classical methods, belief propagation and so on?
So I would say that in supervised learning, the reason why this deep supervised network works so well is that we are not trying to impose our idea of what kind of internal representations it should use. We are just giving it enough capacity to represent the computations that are needed to get from the input to the conditional probability of the output given the input. And I think that this is the kind of leap of faith that we need to do in order to get unsupervised learning working properly too. We have to be able to let go of the idea that, yes, we want to model our data distribution with this kind of parametric model and so on. I think it's much better to rely on the powers of deep learning.
What if the model class is non-parametric? I mean, I agree, if you shoehorn everything into a simple parametric form, it's not flexible. But suppose we have, we have a Bayesian oracle that can do exact inference.
In some sense, this is a Bayesian oracle.
Okay.
So let me rephrase a little bit what Harry has said. So imagine you consider a supervised learning task, but you imagine that the correct graphical model for this should include some latent variables which correspond to what you think are the underlying explanatory variables and so on, and from which you can derive the answer if you were able to do a sample from the posterior. The problem is that representing that posterior distribution in the ways we usually do it with graphical models is often very difficult. We have to resort to all kinds of approximations, and often we have to end up sampling from that posterior. If that posterior distribution is complicated, we may be in trouble. It might take a lot of time, and we're going to have potentially poor approximations. Instead, if you think about what's going on in these deep supervised networks without any explicit distribution in the middle, it's like if we have this deterministic representation implicitly of what these latent variables would be capturing, as far as what concerns the task, of course, throwing away the things you don't need. So you avoid these approximations, and you only concentrate on the approximations that are relevant to the task.
I would want to add one thing, since you asked my opinion too, which is that, so we've heard a wonderful talk by Rob Tipsirani, which was about inference. So it seems that prediction tasks can be done quite well, but inference is something of its own. It seems hard to infer causal relationships between variables if you don't have a graphical model and if you're not actually doing probabilistic reasoning over this graphical model. So I think there's room for both, I would say. There's a question there.
Yes, I'd like to touch a little more on about this learning like a child question and get a little bit more at what's the hang-up? You can take only a few million neurons, and in 1 week it can learn thousands upon thousands of objects. And as the father of a 6-year-old, I can tell you it would take a long, long time for them to reach that point. If you were to build a network that were to take 6 years to properly train, what more would you need? Because I claim that if you wanted to work on a graduate student lifetime, you're aiming for superhuman abilities.
Great question.
Well, I think the comment was not to learn faster than a child. It was to learn like a child, just because it may be interesting to do so. And I think we still haven't discovered where the ImageNet training data is encoded in the human genome for us to have that capability from birth, and whether it can be just done in an unsupervised setting. But in particular, children learn, I think one of the famous cognitive science results is they learn only from positive examples quite well. And very few machine learning algorithms do well in that setting. So that's just an example of the kinds of things that I think are interesting.
And they learn mostly unsupervised. I mean, in the first 2 years, you don't get much supervision because language isn't really there sufficiently.
That's debatable. I mean, if you consider motor and food and...
There's some, I mean...
What is supervision may be the most important question to answer, right?
I mean, not the kind of supervision we get in ImageNet.
Precisely.
So if you had unlimited resources and unlimited time to train, what do you think you're missing to get you to that point?
A short answer, because we're almost running out of time and there's some few more questions. Is there anybody?
I still don't understand the question, because you seem to be focusing on accuracy, not the way
no, not on
happens.
accuracy, but on the process. One of the things that stops you, for example, from really training well is the fact that you have finite resources and a finite amount of data. But a child is learning for years and years and years and years before they get to the point where they're competent enough to learn some of these things in a few examples.
But it's all unsupervised or very weakly or weirdly supervised, so I don't think our algorithms quite can handle it.
Yes, so what are the fundamental advances that have to be made outside of resources?
Yes, so my answer would not be so much about what needs to be done, which is probably a combination of having more data, having a lot more time to do the training, and having more powerful machines. But I kind of feel that for children, like, you don't just want to think about how many years they've had of their lives to learn, but also you have a lot of things which are encoded. So one example I like to think about is that if I draw a stick figure of a new animal for a kid, they'll probably be able to recognize that animal when they see that animal in a photo or in real life, even though it doesn't look anything like that. I cannot draw very well. But you already have the representation that allows you to do this transfer.
So I think we should actually stop here. I'm very sorry for those people who lined up, because the food is being served, and I would hate for you if the food is gone, because I kept you here. But let's at least thank our panelists here and give them a big round of applause.
Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.